This is where the experts are. This is where the leadership is.
And here All right. Yep, there we go. Dylan, how's that sound? Okay, Dylan, why don't you talk for us?
All right, I hear you. It sounded a little hot on my end.
Okay, yes, I see that. Let me see if I can do that here because we adjusted this. Yes, let me. There. That should be a little
Oh, there,
better.
that sounded much better.
Excellent. All right, and we've got you here nice and clean.
Nice and clean, sounding good.
All right, let's go back to Herbert. He's trying to figure out.
Oh, we're getting an echo here.
It's me, don't worry.
Alrighty.
Is it on? Yep. Yeah, it's past 10, so we might just start. So thanks everybody for joining. This is the CPU isolation micro conference. I'd like to first thank our sponsors. We won't be here if we weren't for them. We have a few topics today. We don't overlap pretty well with the break at 12, so we'll see how we are doing actually with the actual discussion and see if we can adapt or just go there and have a break. And I don't know, I guess without further ado,
What
Frederick,
time is it?
yeah, it's
All right.
10, so we can start.
Okay.
Frederick, first one. So
Yep. Okay. I have my microphone. Thank you, everyone, for coming to this micro conference. We are going to start with slides. This is not the okay. Okay. We're on the break. Thank you, everyone. Okay. Thanks. Okay, so the initial title for this presentation was CPU isolation, how to tune it with or through CPU sets, I think. But doing the presentation, I realized some mistakes made. I mean, this is the point of doing presentation, right? And yeah, so I made it a little bit more generic, like how to tune it on runtime. Maybe CPU sets, maybe using something else. So to begin with, what is CPU isolation? So the point is to avoid disturbing a CPU and offload or move some work executing on the CPU we want to isolate to a bunch of CPUs that we can name housekeeping CPUs. This is currently only boot defined. So the only way to tune a set of CPUs to isolate is only through these three kernel parameters, no hertz full. This basically isolates most of the work that can be isolated. RCU no CBs is only about offloading the RCU callbacks, processing and invocation. And isol CPUs is only about isolating a CPU from scheduler domains and avoiding all the load balancing. And as a side effect also, it isolates a CPU from unbound timers and work queues, which no hertz full does as well anyway. So housekeeping is kind of the reverse of isolation. So when a work is exported from an isolated CPUs, it goes to a housekeeping CPU. These isolation features are all grouped into CPUs. Yeah, CPU masks. I guess one of the most famous one is the no hertz full mask, which gathers all the CPUs that stops their tick in user space. But you can also find CPU mask for unbound timers, unbound work queues, and unbound case threads. So all these things are unbound works that can execute pretty much anywhere, preferably on some node closer to the CPUs that enqueue a work. But anyway, those are unbound works, as opposed to, for example, per CPU timers or per CPU work queues that cannot really be offloaded or exported to other CPUs. There are other features that are a little bit more obscure, such as managed IRQs, which I never really understood what this is about, but Thomas might answer if you have questions later. RQ, yeah. um, so why bothering with all these separate CPU masks? So the point was to be able to individually tune all these CPU masks separately through, for example, CPU sets. Why in the hell do we bother? Would we bother only tuning, for example, just timers or work queues CPU masks? The answer is just that I don't know. I cannot figure out any possible use cases. The most famous CPU isolation use cases are those where we want to move away every possible work from an isolated CPU. But I can imagine some setup like HPC where you might want to disable the tick in user space just to avoid some um, overload. I mean, some yeah, if you want to keep the CPU cache hot and not have the timer ticking all the time and trashing the cache, for example, or just consuming CPU time 1,000 times per second. So maybe some people might be interested, for example, in disabling the tick in user space, but wouldn't care about moving the unbound timer work queue. So there you go. This is the reason why I would like to prefer being able to have it fine-grained. So one of the first attempts I tried was to start with RCU no CB. RCU no CB is about offloading callbacks, invocation, and tracking in RCU to another CPU, so that a CPU, well, traditionally a CPU executes and tracks the callbacks from the CPU that enqueued the callback. So the point here is to move away this work to other CPUs so that the isolated CPU is not disturbed. Being able to tune at runtime this CPU mask, which is currently only tunable through the kernel parameter RCU no CBs, being able to do that at runtime required a lot of work. I thought only 2 months. And Paul told me, oh, I can do that. And I said, oh, let me try. I'm not familiar with RCU. I want to see what, what this is like. So it took 2 years, eventually, for me to be able to do that. And in the end, the interface to change the RCU no CB CPU mask using CPU sets was only 4 patches, which I posted a few months ago, like 2 months ago. And this patch set had quite a reception. The first question that was raised by Tijun was, why are we using CPU sets and not sysctl, for example? Because CPU sets is about hierarchy properties on CPUs. Yes?
He should be able to unmute himself and speak, and we'll hear him.
I don't know how this works.
Just Peter can.
Oh, okay. What? Where? Later? Oh, okay. Yeah, better.
Peter, you had your hand raised. Can you unmute yourself and speak to us? We should hear you.
Yeah, I'm here. I see that this next slide already has my suggestion. And then I sent an email as well. Just start with a simple knob and extend the API if and when there is a use case. Don't start with a split out thing.
Sorry, I did not understand the question.
Well, in the previous slide, you suggested starting an API with all the separate masks split out and available to the user, and I said that's mad.
Mm-hmm.
And this
So you-
slide already says this. So yeah.
so yeah,
Only extend an ABI if there is a use case. If there is no use case, don't do this.
right. Yeah, so yeah, I'm going to talk about that in this slide.
Fair enough.
Yeah. Yeah, that was, yeah, I was about to talk about that in this slide. So the thing is, yeah, indeed, you, Peter, suggested that we have an all-in-one switch to be able to isolate everything, and if should the need arise later, have more fine-grained interface, right? Right. Uh, and at that time, we didn't have actually a use case for just tuning RCU, no CBs alone. But recently, I realized that RCU no CBs is not only used for isolating CPUs, but also to save power on Android. And in this case, you don't really need no hertz full and all the other isolation features. So this is why I'm considering again having an interface, at least for RCU no CBs alone. And yeah. So that was one of the reviews I had. And Tijun also didn't like the fact that we are dealing here with flat properties on CPUs, whereas CPU sets is about hierarchy, and hierarchy are not really relevant here.
Well, CPU
No.
sets is also the place we do scheduling partitions. And
Yes.
they nest up to a point, but if you do the isolation thing, that's partitions of a single CPU. They don't nest either.
Yeah, right. Yeah, they don't mess anyway. But
Can't you have like still multiple levels of isolation? Like you defer, I don't know,
no, not really. I mean, at least I cannot figure out any scenario with that. So
I'm not sure if it makes sense, but let's say you have your system, you split the CPUs in half, and then you delegate like both halves to, I don't know, a different, I don't know, manager thing.
different isolation
And then
properties.
that thing
Maybe.
can actually
Yeah.
say, okay, I want only 2 CPUs out of the 8 that you gave me to
Yeah.
just manage RCU no CBs, and the rest. And then the other thing can actually configure it like 1 or 4 CPUs instead of 2.
Yeah, indeed. That could be a tricky setup. But that's possible, indeed. Yeah. That could make sense. But this is not something that couldn't be implemented using a flat property setup. And the other concern that Tijun had was that we are, well, CPU isolation, if you dive into the details, you're diving into really gory kernel details, and Tijun didn't want to have those exposed in CPU sets because it's more about very high level properties. Whereas here with CPU isolation, we may be dealing with very fine-grained kernel internals, like work queue, unbound work queues, case thread affinity, or so.
Well, only if you make it fine-grained. If you do a high-level isolation feature, then I think it nicely fits in with the partitioning stuff that's already there.
Yeah, that could work indeed. Like, for example, we can gather all the unbound work into a single feature, like unbound timers, work queues, and case thread into a single feature. That would be a high-level exposure, but I don't know if we later need more low-level tweaks. I don't know. So yeah, in this case, one possibility could be using sysctl, which allows for more low-level tuning, and besides, it's also much more simple to use from a user and developer perspective. And also, it makes CPU isolation not depend on C groups, even though nowadays not depending on C groups is more and more difficult. But so yeah, one possible layout could be having kernel.isolation.default, which is an all-in-one switch, like Peter suggested. And then we can later add features like more fine-grained features that would override the default file, the default parameter, like kernel.isolation.rcunocb, for example, which would only override rcunocb. And later we could have kernel.isolation.unbound, no hurtsful, I don't know. So that's a suggestion. I don't know. I don't know exactly what to choose between CPU sets and ccTL. So here is the open questions. And that's it.
From my point of view, I think I will agree with what Peter said, that you focus on isolate the nodes, everything like RCU, no hurtful, and maybe no RCU as they talk about power saving. The other binary green feature, we won't implement until there is proven to be use case for that.
Right.
And I agree that it's better to be integrated with the CPU set partition feature, because otherwise, you will do a separate sys control, it will interfere with what CPU set is doing. So it may make things more complicated, especially if the set of CPU are different. Then we are running into an issue about which one by which, and it just introduce complexity.
Yeah. Yeah, in any case, I think we want to start with an all-in-one feature, whether we choose ccTL or CPU sets. That's for sure.
So, but your last point would be basically in favor of implementing, about having the interface on C groups, right?
Yeah. Basically, on top of the current partitions feature, so you don't separate, you don't add a separate thread standalone, but it's an attribute into the partition that return off additional feature for those CPU.
Yeah, so that's the advantage of using CPU sets, is that you're, well, there is already the sched load balance file in C group V1.
Yeah.
Doesn't exist in V2, but there is an alternative, a recent one. And yeah, we could join that kind of partition with CPU isolation features. So yeah,
that partition already had handled the hierarchical aspect, that you are able to have limited hierarchy if you really want. So you don't want to reinvent the wheel.
Yeah, that's a good point. Another question or opinion?
I was actually thinking about the timers. For what I've seen, at least in the real-time use case, what we usually do is like we tend to have the timers handling on the housekeeping CPUs, but for certain timers, we like them like affine to the CPU where the real-time task that actually queues the timer is actually running. So I guess the synthetic use case is the cyclic test. So we run cyclic tests on the isolated CPUs, but then if the timers the cyclic test uses for the clock non-sleep are fine and move to the housekeeping, then it's a problem because the latency is higher.
Yeah.
So basically, I'm wondering how that would be configured, or if there is any relation to this thing.
I don't know. I guess those setup can already be done using the isol CPUs or sched load balance file in CPU sets. So I guess currently we already have some kind of interface for that.
There is, I think, a sys control thing called timer migration.
Oh, there is.
So maybe I don't know if there is a point in favor of going this way, but
Okay.
um,
Yeah. Okay. There is a file like that. It's in sysfs. Or?
yeah, sys control thing. Yeah,
Syscall. Oh, it's
yeah, I think so.
Okay. Mhm. Right.
The idea is to start with CPU sets now. That's the next step. The conclusion of this discussion.
There is no conclusion
Okay, but-
as I see it.
But it would be nice to have at least a partial answer. What would that be?
It seems that people are a bit more interested in using CPU sets, I guess, because it's more integrated with the existing isolation feature, which is scaled load balance, disabling load balancing, which has the same effect as isol CPUs. So I guess I'm going to continue with CPU sets. As usual, I'm going to post a half-baked patch and see the reactions. I guess that's the most efficient way to get an answer anyway.
I guess another point of my impression is that for the tuning that, for example, we do on OCP, I think, yeah, we actually tune in some sys control stuff, but I think most of it is using C groups. I'm not saying that it's not possible to tweak both, but maybe it's easier to have. I mean,
To have both, like both.
no, I'm saying that I don't know, can be perceived as I should find what I need to tune like on the same place. So maybe this is another point towards
Right.
using CPU sets, and so it's
Yeah,
everything.
but one worry I have is can we expose RCU no CB in CPU sets? Because we will definitely need a way to tune RCU no CBs on run alone. I mean, on runtime. I know, right? That would be useful, right, for Android and.
Because, as for Android, so we do want to optimize, so it's obvious. So it's from power point of view.
But would you be interested in having it tunable in runtime?
Isolation, yes, but RC,
But not RCU no CB?
RC and OCB, we do enable it constantly, and we don't switch it on runtime because it doesn't make sense for power savings at all.
Okay.
One thing I wanted to try was, if we can switch it after boot completes, because at boot up, we don't care about power that much because like the system is already so power hungry. So
just to see if
because like I know that it's not much, but there's some like 2 or 3% improvement in regression in boot time with no CPs.
That's significant.
Yeah, so I want to try that. We didn't try it out because
you can try it already. I mean, there's just a function to call that you can try right after the boot.
Yeah, but
and see the difference.
Yeah, but that won't work because boot is like defined for us like after init loads and everything starts up, right? So it's according to the kernel, everything is booted, but we're still booting.
Yeah.
And so it's the kernel is I think like half of the boot process, and then after that everything else starts up. So and then we get to the login screen after quite some time. But I thought your question is your question about tuning the mask dynamically or just tuning the whole?
Tuning just the mask.
Just tuning just the mask. I think we don't do. I thought most people just offload everything.
Yeah, I think so.
So
okay. Okay, then in this case, I can just start with directly with an all-in-one file in CPU sets. And
but are you sure Tejun would be okay with that? Or that's the kind of I thought like he was not okay with kernel internals.
He was not entirely close to the idea, but well, we'll see. After all, the interface part is only is the easiest part, because being able to tune at runtime no hertz full, that alone is going to be 20, 30 patches. That alone, and not even considering all the unbound work to offload and stuff like that. So yeah, anyway, the interface is going to be a detail, but yeah, we'll see. We'll see what he thinks, and okay, if he refuses, we can still move to sysctl. It wouldn't be too big a deal.
Or maybe keep it at boot parameter if you don't need. But I guess for your use case, you need it to happen dynamically.
To have what?
To change the mask after boot.
Yeah.
So I guess boot parameter won't work.
Just the boot for
Yeah.
RC and CB, right?
Well, for the other masks as well that you mentioned.
As well, yeah.
Yeah.
Well, we need to keep the kernel parameter anyway, yeah.
Question? Not, that's it. Our speaker.
Okay.
Thank you.
Thank you.
Right. So we're running early, which is fine because we'll have more time for the break. Next one is Marcelo. So yeah, please go.
Is about improving the isolation or removing some of the sources of yeah, right. Removing some of the sources of interruptions. And so the current situation is that there are a number of call paths which can interrupt isolated CPUs. And we rely on user space behaving nicely for interruptions to not occur. And then this is a little off topic, maybe a little off topic thing, but I decided to write it either way anyway. So that if you have distinct interference sources and they align in time, then the interference on isolated CPU might sum up. And I guess that for some workloads so far, that was not considered too problematic because the consequences of violating latency are perhaps acceptable, but it seems that for other workloads like industrial automation, this could be a problem, so it'd be better to deal with them. So this talk is about some of those call paths that can generate interruptions to isolated CPUs are executed from user space, and so they can return errors. And so what we are proposing is to introduce a new CPU mask and then trying to use the name interference rather than interruption, because interruption kind of is ambiguous with IRQ interrupt, right? So, so it's a new CPU mask, and called block interference CPU mask with a bit set for the CPUs, which should have such interferences blocked. And then on top of that, we introduced fail variants of functions that interrupt CPUs with the variant checking whether the CPU is marked as block interferences, so there's a typo there, and returns an error. So we would create fail variants for the families of functions that interrupt CPUs. And this CPU mask is to be written from user space after system initialization. So because the initialization process might require code execution on this interference block at CPUs. For example, MTRR initialization, REST control file system initialization, which will do MSR writes and other MSR writes. So the pattern that seemed natural was you grab a lock per CPU read-write semaphore, and that was chosen because it's very cheap on read. Then you call one of those functions, the fail variant. Then you unlock that per CPU read-write semaphore. And if there's an error, sorry, there's another type of error, it should be if error at the end. Then you return error to user space. And the second pattern is where you don't want to check the errors from the functions that generate interruptions. So you grab the lock, then you directly you find this target CPU. Then you check if that CPU is part of this mask, of this blocked interference CPU mask. Then return error to user space. Then you have the code that would interrupt the CPUs, then unlock that per CPU read-write semaphore. Yeah. Yeah, so those are the examples, yeah. So for example, so there I did 4 on the patch set that was sent this week. There were 4 conversions. So one of them is a simple one, which uses the first pattern. So rather than calling, so this is a clock events on bind when you do a write to a CSFS file to change the clock event device, and it will get here. So you grab the lock, call the fail variant, which will check the CPU mask and return error if it's set, and then unlock and return the error. Right? This one was also on the clock subsystem, but to change clock source from user space, and it becomes a little more complicated because it's called from a path where you can fail and from a path where you don't want to fail, and then you need to handle that separately. This one looked quite ugly, but I don't know if any. You're saying that if you're in user space, for example, you don't need stop machine could skip those. I don't get it. So what I understand is that stop machine will call will interrupt all CPUs on the system with the function that So when you you do right. So so yeah, the thing is in under this, if you follow this code path, tclock notify will call, we end up, yeah, so it's calling stop machine. So I'm not sure the point really, Frederick, because do you mean that we could change this code to use something else other than stop machine? So you're saying that user space should not try to change the clock source? But then it doesn't know, so user space is exposed an interface and it doesn't know which things do what, right?
Yeah.
So
I know that
how,
requires.
how would we, this is a way to avoid, like you ensure by having this code that even if user space calls, the clocks are changed. This is like a bad example, really. But
Maybe, but
I can give you another example, other examples that you don't have control of all of user space, maybe, or you don't have control of if someone logs into the machine. That's then you're going to say it's difficult, I guess, to have a system where you log in and can only run those and those things, right? There are situations where people end up doing things, and you want to have some sort of guarantee that the CPUs will not be interrupted, right?
Okay, but
You know what I mean?
yeah, I see what you mean, but I really think that user space workloads involving isolation really need to comply to some basic things not to do.
Oh, I see your point. That would be a nice thing, but
Yeah, that would be nice. Yeah, I know.
yeah, it would be nice if it happened, but people want to, they have their, like Edge, for example, they have their machine and at the edge, and they have a single one, and so they need to run some applications on the system that's running isolated applications as well. And then if you want that, so you're going to say, you could say, okay, don't run anything. This is a special type of system. I don't want anything else to run there. But it becomes difficult to do that, right? You have to have people know about this, and then there's a special system that you have. It's not like, oh, okay, I can log into the system as any system and run things, etc. Go ahead.
Okay. Does it work? Okay. So I think that the case that Marcelo is mentioning are those systems that use Kubernetes and OpenShift, where you can have multiple types of workloads, and one is not necessarily aware of the other. And so in this case, it happens. So it happens to have a workload that's not aware of that CPU isolation. And even these workloads with CPU isolation, they come and go dynamically. So that's why Marcelo is trying to refer to this case.
Yes.
That's his use case.
As an example where I think it's easier to do this in a centralized location than to change maybe change a way to interact with the system.
One question, why, so this is called when you are changing your clock source, and the previous one was when you're changing clock event. How you want to change your clock source if you want to be isolated and not disturbed by anything else?
Yeah,
From the beginning, I would say.
This example is more of, this one is more of like an example, because you wouldn't normally do that.
Yeah,
but
that's my point.
MSR reads, people do, and we've seen on a few. And so this is just maybe examples on the usage of the API, but which is not realistic. Like you couldn't think of any case where someone would do that, and neither do I. But there are other cases where the following examples. So
Okay,
let me
maybe
go
the
to the
next one.
next one. So perf, for example. So you're attaching a perf. context to a CPU or to a task, and then the task is running on a CPU. And maybe this could happen by an accident, let's say, right? And if you block it, then this is one example which is more realistic. There are other ones as well. So this would be the
I don't know where this is in perf. What?
This is the perf event open or open event.
Okay.
Called,
Yeah.
where you're creating a perf context. I don't know.
Yeah.
To monitor
creates a
some
perf event
and then you have to interrupt the CPUs to maybe I think
right.
enable the triggering of the monitoring of the performance architecture row events. And then you do that through an API.
Yeah.
So in this case, I just changed the case where there's no task, so the person has to pass a mask with a CPU perf -c, and then you would say, okay, if you're aware that this system has isolated applications and even CPUs, you wouldn't never do that. But people might do that, or this applications might end up doing that for some reason or another. Then we want to block that. So that's just the pattern 2. So it's checking before it grabs the per CPU read write semaphore, then checks all CPUs that it's going to send IPIs, and if there's any one of them set in the mask, it returns an error. And the other one that is perhaps more, well, this one we haven't seen in production, but if you do write to proc MTRR, which happens when you're starting the X server, for example, maybe there are other situations, then the same pattern too. You check if any online CPU, because it's going to interrupt all online CPUs. So if any online CPU is on the also blocked interference CPU, then we return an error. And then again, there's other cases like MSR writes, and that we see in production, MSR writes, or changing things like CPU frequency or locking CPU frequency. And there's also WBIVD, which is caching validation, which happens on some code paths with graphics card. I haven't looked deeply into those, and I don't know exactly when they can happen, but I know that at least they can happen on initialization of graphics cards. Yeah. So one thing that was not clear and that looked quite hacky was the location of the CPU mask to be exposed to user space. And currently is in the BookFS for the pad set that connects with the previous talk. So there was a location to maybe a more official location to have this kind of interface exposed to user space. It would be nice. And yeah, so that's about it. And I was wondering if anyone has any other comments.
I guess it could be integrated into the housekeeping stuff. Which so I know that there is the issue that during the initialization you don't want to work, but only after initialization, right?
Yes.
But I guess we can do that with housekeeping. I mean, having that CPU mask exposed with the rest in the CPU set, for example.
Right, but
unless
it should be this initialization, you were thinking it needs to be user space controlled. Like, for example, this MSR writes that you might want to do on a CPU or MTRR writes, you would do it. It it's not like late init call time, but at some user space triggerable time. I'm not sure if those how.
And this is not something that a user space could tune using CPU sets?
Sure.
Yeah.
As long as it can tune it at a given
Yeah.
point in time that it chooses, then could be CPU sets. But and then also it's kind of weird to have it as a separate. Should it be a separate thing, the CPU mask, or maybe just along with RCU no callbacks, or
Yeah,
I don't know.
I think it can go with the rest. There may be a whole CPU mask for all the isolation features in the end, especially if we modify it through CPU sets in one go, then let's just have one CPU mask for everything.
Yeah, but then you would need some other user space triggerable or writable interface to enable this, right? Like use the CPU mask that's being used by isolation, but this feature is disabled until someone writes enables it. You see?
Oh, so there are cases where this feature could be disabled while having the rest of the isolation
Yes.
running. Oh, okay.
But I don't see any use for disabling it on runtime. It's just that this thing you might need to interfere with this isolated CPUs. For example, if you want to do REST control file system initialization, you need to write some MSRs there, like to set up the cache reservation and everything in user space, and then that will generate IPIs or queue work, IPIs, and then you want to allow that, right? And then after this is done, you block any further APIs from the MSR or any of these paths, paths that can return errors.
I just wanted to point out regarding the earlier claim of user space just shouldn't do this. While we all might like user space to be perfect, bugs do happen, and it's nicer to see an error message than to just have latency spikes show up that are hard to debug. Isolation parameters are easier to audit than the entirety of your code base.
Yeah, exactly.
Is it working? Yeah. I think, it's a general question. I guess, if we introduce this, current application will basically see errors reported when I try to do stuff that was working before, right? So my question would be, how do you expect those, current app would adapt to this fact that maybe from one day to another they cannot really?
That's a good question. But we maybe see failures like something will fail on the system and it will stop working, right? Something will someone down the chain will complain that something is not working, but you prioritized, and I don't know. I also wonder what kind of things will happen, and I hope that there's nothing bad can happen, but I don't think so. And then you'll have to address that issue, right? Yeah.
Yeah, and I guess a follow-up question would be.
So, for example, let's just try to think of an example. Maybe like resource control file system is set up. So you set up a mask, and one of those failures might be like you get latency violations. For example, there is the cache, the resource control. If you don't check for errors in your initialization scripts, then they will fail. The initialization will fail, but you have a system that doesn't have cache allocation done properly, which causes the latency failure. So.
Yeah, and I guess as a follow-up, I would actually wondering what sort of information, so about why something is failing, is getting back to the application. So I don't know, I mean, for what we are seeing, basically, I guess what we usually do is that, okay, we realize that there is, I don't know, an API serviced by an isolated CPU, and then we go and track what basically generated that thing. So I was wondering if a useful addition to this might be like, I don't know, like a debug or more like verbose mode where we can actually give back the application in some way what actually caused the failure, so that can be
Right.
fixed, right?
Yeah, I was thinking of adding a print K, maybe, print K. This, if you have return an error due to this CPU being on CPU mask, on the blocked interference CPU mask, then you do a print K. But then I thought about logs getting filled.
Yeah.
So, but yeah, also that thought.
Yeah, I have a question. If you are able to block IPI, for instance, there are some critical IPI like when you change the page mapping, you usually need to send an IPI to the other CPU to flush the TLB and load the new one. If the other CPU can't do that, it may crash the system.
So the thing is, the idea is to convert the sites that can return errors with this. So then the ones that you can't
Oh,
have
so
them
you
fail.
allow some important call to not allow to fail. They always pass
Yes.
through, right? Okay.
Yes, the SMP call function single interface continues the same. If you don't change it, you get, yeah. But maybe I guess it's like maybe 30% of the SMP call function sites can be converted. So you still have a lot of them that you need to think about, maybe one case by case basis, right? To
So that means it did not actually block the interference. It just reduced the interference, right?
Sorry, can you repeat that?
Because you allow some to go through and some block the other one. That means you partially block some of the interference, but not actually eliminate them all, right?
Not all, no.
Okay.
It's
Yeah, because you use the word block, it seems like you are blocking all.
Yes, that way the block name is like a bad name. Can you think of a better name? Maybe yeah.
Housekeeping is not confusing at all.
Yeah. Yeah, but that's a confusing name. I agree. So I don't know what the better name would be. But like selectively.
Yeah. Maybe you use the word reduce interference or something like that.
Selectively block?
Reduce some of the interference, but not block all of them.
Yeah.
Yeah.
So selectively block may be a better, more meaningful name, you know?
What would be useful as well is either some kind of a tunable or maybe a BPF script or something like this. So when you run it or enable the tunable, you would get extra log message, which would tell you if one of those paths which can interrupt an isolated CPU was triggered, and if it was, especially from user space, what was the application piece name and so on.
Yeah, right.
Because that's the issue we have quite often when we deal with this interruption. We end up chasing, what was it caused by?
Right.
And if you're already identifying all of the paths, I don't know, sysctl, and then you can just go to a log and check like, oh, this is the app which used this syscall or whatever, which caused the interruption. That would be great.
Right, exactly, yeah. So we thought of that too, and we wrote a tool, and it's called RT-trace-BPF. So if you look it up, that does that. And you get a backtrace as well of the task that's interrupting, and it's helpful because you don't have to do all the tracing and everything. But it should be perhaps integrated into the kernel, so you would have seen it already, Yeah.
And what about the so there was an idea to delay the SMP call single function until a task comes back to the kernel.
Yeah.
So what about that? That maybe could be an alternative to.
Yeah, so I think for some of the interruptions, like the TOB flush,
It doesn't work everywhere, of course.
Yeah.
Yeah.
So it unfortunately the person who was working on that, Nicholas, he's moved, changed companies. So we need to get his patch set, which still is maybe has some things to be fixed and tested and finished, and then send that patch set. But yeah, so unfortunately, would be working on that, but he moved. our
And
company,
see how
so-
many colors we can convert to that delayed API and see then the rest.
I don't think any other, well, the ones that we can think of is the TOB flush, right? Makes sense for kernel addresses, then the code patching, right? And maybe anything that would be used by anything that would use when you enter the kernel, I suppose, but anything might be a hard word, I don't know. Yeah, so, yeah, I guess the cases that are there, the cases that are there, the TOB flush and the coder writes are the ones that are seen most on traces when you run like a stress application alongside the isolated one. So, yeah.
I mean, another related question. So when you enable this feature and for some of the calls you end up returning an error, which you didn't in the past,
Yes.
what could be useful is, I mean, log message, maybe if you enable it, but what could be useful is have some kind of a static BPF probe, a single probe you could attach and get an information every time you return an error because this is enabled and which application was trying to.
Can you repeat that?
So
what
when
would
you
be
enable when
useful?
you enable this feature, right?
Yes.
And you start returning errors now for some of the calls.
Okay.
What would be useful, I think, is if you could provide a static BPF probe, a single probe, essentially, a hook, if you like.
Yeah.
So you could very easily trace which applications are now failing and because of what call.
All right. Yes. Or now that you mentioned maybe trace points, right? Like
Yeah.
trace, fail.
Exactly.
You know, yeah, trace point that is much better than a print key.
Yeah, exactly.
Right. Yeah.
That would make life way easier to trace down those applications and see exactly what they're trying to do.
Yeah, that's a good point. Thank you. Yeah. So, yeah. What I had to present. Any other thoughts or comments?
Questions? Okay. If not, thank you, Marcel. Yeah.
Thank you.
Thanks for the up, I think, is Joel and Diego. So yeah, we are actually a little early, so we can maybe wait 5 minutes. Next one is Joel. So yeah, we are about to start like in 5 minutes. So if you want to take a quick break, we'll be starting at 15. Just saying. So yeah, I think we can start so that we have also more time for the break. Yeah, they're here, so yeah, that's right. You have that one, and you can use this one. Yeah. So yeah. Right. Yeah, I think we were. So yeah, please take it.
Hello. So, yeah.
Hello. We can get started. My name is Joel. I work at Google in the Chrome OS group on performance, power, scheduling, RCU, stuff like that. And you guys want to introduce yourself?
Yeah, quickly. Yeah, my name is Vladislav Reski. I'm working in Sony Mobile, doing same kernel, performance, power, thermal, some things like that.
Hi, my name is Rishikesh Kadam. I work for Intel. I've been working on firmware previously in SoC power management, firmware, and so on, and most recently working on power and performance optimization for Chrome and Linux devices.
Okay. So yeah, so this talk is about RCU and some room for improving systems, the way they use RCU. We can keep this like discussion and interactive sort of thing. Obviously, we won't go too much into how RCU works, and hopefully everybody knows that part. So the two issues that we have been working on is how to improve the power efficiency in the system that is mostly idle, and how some amount of RCU activity can disturb it. Just to be clear, that's not RCU's fault. That's whatever is making RCU do work. Paul wanted us to mention. So RCU is, the most popular use case is, the concurrent read and write of data structures, which is possible because a copy of the object being written to is created, and then you swap pointers and wait until all readers have exited before you can do a garbage collection. However, that's just one use case, and there are many uses of RCU. But all of them have the same need the same basic tools, which is you need to know when a critical section starts and stops locklessly, and you need to know when to start waiting, and you need to know when to stop waiting, which is when all the readers that existed when you started waiting have exited. And this can be accomplished with callbacks. So you queue a callback when you start waiting, and RCU will check all the CPUs, make sure there are no readers left, and invoke the callbacks. So the timer plays an important role on CPUs on certain RCU configurations, which don't use NoCB, config RCU NoCB. So the timer tech has to do some amount of work, check if there are any readers on the CPU, on the current CPU where callback is queued, and also it has to check whether all CPUs have checked that they don't have any readers as well. Only then can callbacks be executed. And this also, some of this doesn't have to happen in idle. However, if you queue callbacks on the local CPU, you still need the tick to be active so that it can, it can check if all CPUs have reported that there are no more readers anymore. So you still need the tick. So this is the observation that because callbacks were queued, the tick cannot be turned off because you have to keep checking if all the other CPUs are done, right? So turning off, turning on, well, okay, we'll get to that. You can just talk about traces, so show a trace with this issue, right?
Yeah, so this is an issue I observed earlier this year. So the snapshot on the right-hand side is the kernel from kernel shark during local video playback. And the vertical blue boxes is where are the frame boundaries for the video playback. And that is where inside those blue boxes is where the audio video decoding is happening. And then between the blue boxes is the idle period is where the CPU should go to low power state. But then the red boxes is the issue here. So what we observed is there were instances where the kernel stick was kept on by RCU. And so that was a problem. It was causing a large number of fakes and preventing the SoC from going into low power mode. And so, yeah, I think that's pretty much. I think next you will talk about why it was keeping the stick on and so on, right? Yeah.
So as you can see in the trace, he just showed also that the tick is kept on when CPUs are idle. And so why does RCU do that? Or why would people have RCU configurations that do that, right? If it's so harmful to power and stuff like that. And the reason is because it can be useful for large servers and busy systems that which queue and dequeue a lot of callbacks and invoke a lot of RCU callbacks because you get the benefit of the cache being hot, right? Because everything happens on the same CPU. You also have the benefit of not having to queue a callback on one CPU and then wake up another thread on another CPU. Miss any other advantages? Yeah, and there's no lock contention as well. So because everything's happening on the same CPU, the callbacks are executed in soft IRQ, so you don't need to hold the list lock to DQ callback from the list and execute it. So there are advantages. However, for power systems that care a lot about power, like battery powered systems and all, keeping like the tick on during when the CPU is idle and not doing any work is like unacceptable. And in this slide, you can see that just turning on config RCU no CB increases gives like a 12% power improvement with video playback use case. And basically this was observed on an Intel platform where the deepest package C state has like 25% more residency, giving that 12% percent improvement in power. So yeah, so I wrote a tool called RCU Top to observe. So this here's another observation. Even after turning on config RC no CB, another observation we see is that callbacks are still constantly queued on a system that is like almost idle. because various things in the kernel are like, constantly queuing callbacks, and RCU is then like trying to start and end grace periods and things like that. So RCU top is like a BPF tool I wrote, which we hope to merge into the kernel sources as well, which will show you, at a high level, what are all the callbacks on the system that are doing this. So this has been really useful. In this slide, I show there's a trace that Rishikesh collected where we see that with the Chrome OS display pipeline, we see that every 16 milliseconds, we see RCU callbacks being queued. And this is because the graphics buffers are represented as file descriptors, and they're like open and closed every frame. Yeah. Question?
Yeah, I was actually curious about the tool since you showed me yesterday. I was wondering if there is also a per CPU view of the where those sort of things are queued. Because, for example, for the
there is not right now, but I think that could
that would
be
be
useful.
nice, right?
We should do that. Yeah.
Because especially for the isolation, when we want to check that the isolated CPUs are not.
Yeah,
basic
that's a
service.
good point.
Yeah, okay.
We should do that. Yeah. Right.
Just out of curiosity, is it based on RCU traces?
Yes.
Yeah.
Yeah. So the
Okay.
invoke callback and the RC callback trace points. That's why I moved it before the bypass list queue happens, because it wasn't even being called, and that's in my path set.
So yeah, that could be a good candidate in the tools.
Yeah. Yeah. I think so. Yeah.
Does synchronized RCU, like a synchronous call, look like in RCU top? Does it get labeled as such, and
Yeah,
can you tag who the caller of it is?
Yeah, it shows something like Paul should know the exact function, but it was wait RCU or FN or something like that. So it's internally implemented with call RCU.
Right. I'm wondering, do you label where synchronized RCU was called from so that you know where that call is?
Yeah, the trace point doesn't have that info, but yeah, in those cases, yes, we don't know where where it was called from. Maybe. Yeah. Maybe we can use some BPF magic or something to figure out.
Yeah.
At least ftrace can dump the stack, so maybe we can get that from the tool or something.
If I understand the question correctly, I guess we can make use of built-in address 0123 to understand the caller, and probably we can extend our tracers, RCU specific tracers with such information. It would be, by the way, good. Yeah.
So you want to quickly talk about Android logging and how you saw it? So
Yeah, maybe I will talk briefly, but I will skip this because we don't have so much time. Yeah, about Android. Yeah, I'm about to talk about Android, and we see that especially in idle use cases for Android specific use cases, we see that RCU might be quite active, even though the system is idling, and this is not good from better point of view. And for example, on this ftrace, you can see that in idle use case, most of the wake up belong to RCU subsystem. And if I will also skip this one, and I will, yeah, it will be much more easier to understand. And this is idle use case. It's a static image use case, and you see the traces, and this is RCU batch start traces, and you see that 4 CPUs. So we have a big and little cluster. We have 8 CPUs, and first 4 CPUs, they are quite busy with such activity, RCU activity, for invoking callbacks. And the problems with this or drawback is that we invoke only few callbacks, and actually it's a kind of wasteful. So yeah, it's a kind of wasteful.
The real question is, why is file system?
So it's actually, you know, it's a bad world. So sorry? Okay, yeah, it depends on app, it depends on everything, but there are bad apps and you can do nothing with that. But in our particular test case, I show that login can destroy idle use cases. And for example, a login make use of a lot of opening, closing files, and we see that functions like file free RCU, I node free, by RCU, I callback D free, IVC node I free, AVC node free, as they actually apply such load on RCU subsystem.
Where is it? Thomas that was asking about one thing. I just also want to say is like the question was why would we want RCU on an idle CPU? I think part of it is the fact that this is generic systems. Like it's a Chromebook. Like us, I care about Chromebooks. I'm on the Chromebook team. And we have multiple CPUs, and there's a lot of cases where things just go idle. So it's not like, it's just that you have cases where something kicks off, something goes idle for a while, then kicks it off and goes idle, like the video playback. And because it's just the general way RCU works, it's not like we don't have anything designated as this is like idle and we should move the callbacks someplace else. It's just more like we're wasting electricity because we just happen to pick the idle processor. I think I mentioned, this is one of those things I threw out that crazy idea in IRC, like, hey, can we, when we, in the scheduler, can we just move things off of, like if something's going idle, and is there a way that we can move K threads or whatever off onto other CPUs that are busy and keep the idle CPUs idle, just generic method. So it just means that the normal system is, when things go idle, we just happen to be filling things up and we're not letting those idle CPUs go idle to save energy. So in something like a Chromebook where laptop battery matters, it would be better to move those things off to something that's already busy than to keep and let the CPUs save electricity.
Steve,
does that make sense?
It's worse than that.
So it's worse than that.
Yeah, so that's good. But what he just showed a picture of, and what Rushika showed a picture of, is the entire system has to go idle to get into a really deep power saving
Okay.
state. So you really have to score 100 on this one. You
So
can't
it's-
just, that work, you really want to eliminate it rather than move it.
So actually, so I guess the point I guess we're saying is if the system is idle, do we really need to garbage collect?
Bingo.
So I
So
guess-
that's, I was getting to that. So garbage collect is not the only thing, right? But
Well,
you can
why
use
do we need the
for-
RCU callbacks
Yeah.
to execute?
Yeah.
I mean,
That's,
if,
I'm
if
getting-
there's nothing, if it's, as long as there's nothing that's blocked.
Yeah.
If everything's in the sleeping state, not the task interruptible state.
Yeah, so so I'll jump to the solution. After trying out everything possible to, improve the situation, we believe that the way forward, and we can discuss that as well, is to selectively identify which callbacks are in our observation, there are not a lot of callbacks that are constantly being queued. They're in the VFS mostly. There's some task struct stuff. Some callbacks in SE Linux. But the easiest and the lowest risk way is to introduce a new API that will make that we call lazy RCU or lazy RCU callbacks, where we queue these callbacks, but we don't let RCU know at all that they exist, and we set up a timer. And of course, we are very careful that memory pressure conditions don't get worse or be out of memory. So we have shrinker to make sure that those callbacks are not a secret anymore once when memory is scarce. The RCU top also confirms that when you switch to such an API, callbacks are not executed; they're just being queued. And we see that there's very good power improvement. So on top of RCU no CB, we see another 4% power improvement when using call RCU lazy. Now I just want to mention that another option could have been we just slow down the entire RCU, But I think as Steven mentioned, you have the memory reclamation use case, but you have several use cases that don't do memory reclamation, like switching off per CPU ref count from the per CPU mode to atomic mode. These things are not, they use RCU, but they're not memory reclaim related. So we cannot just slow down the whole of RCU. So selectively identifying these cases that, you know, that don't need their callbacks executed right away is one way to do this. Now the drawback of this is if somebody writes a new RCU callback use case that doesn't use RCU lazy, then again we're back to where we started. That's why I have a point on documentation.
Also, whenever Thomas talks, you should repeat, because I think there are people here that are, or maybe send that off to Thomas so that the remote people could hear your comments. Unless you want to make it private for the room. But the thing is, what if we just did the other way around and make all lazy and just have an call RCU expedite or something?
That still causes regressions because there are things that have like a synchronous use case, but they don't use synchronous RCU. They use call RCU, and they still do some waiting. So we tried that.
We fixed them.
Yeah, that might be one way. Yeah.
Yeah, so basically do it the way, like you said, have it expedite, and when you find a regression, it's a simple fix. You add the expedite in that location.
Yeah, but let me also to be more specific, because the problem here is not, it's also just keep in mind that on our use cases, we see that we invoke only one callback. And invoking only one callback implies waking up grace period thread and then no CBK thread. And it really doesn't make sense. I mean, to kick RCU for only invoking one callback. And this is the main point. So what shall we do instead? We should combine batch request and then process them. And what we see right now is that it's really you can run into situations when you invoke only 1-2 callbacks, and this is not okay.
Well, I mean, could you put
How would you fix the call RCU users who are synchronously doing something and using call RCU, waiting for that callback to execute? It has to be a new API, right? Because expedited will not speed those guys up.
Well, I say RCU expedite. I mean, well, there is an expedite. I'm not saying just add a new, but use the term expedite. I mean,
yeah, but it doesn't speed up call RCU. It only speeds up synchronized RCU.
So I'm saying, could you have like a call?
So add a new API.
Can
basically.
you have like a call RCU expedite?
Okay, yeah,
That's what I'm saying.
So,
When you do call RCU, like there's a lot of times I use call RCU, say, okay, I'm done with this, let it free. I don't care when it's called, just that it gets freed at some time.
Okay.
So, but if there's something that I do a call RCU where I'm actually waiting for it, that would be a call RCU expedite. Say, I'm waiting for this.
Paul has a, yeah.
Yeah, throw the, I can take mine.
Something Vlad has been working. No, just kidding.
Hey, Paul just said, wait, what was the question? Or what did you say, Paul? Here. Thomas.
What's this call RCU expedited? It's new on me. And what's expedited about it?
So, yeah, so I guess the suggestion is that to use diffease till first FQS to slow down the whole of RCU, except for those call RCU users, like the users that need to execute their callbacks fast, use call RCU expedited. And so that way everything is delayed and batched, and that gets you the benefits you're looking for, right?
But which ones are actually asking for being executed fast?
So there's at least one use case I found. There should be others because we see regressions all over the place, but the one I found is this one, where per CPU ref counters uses call RCU to do the switch between ref mode and atomic mode or something like that. And that is used in the suspend path called from block pre-runtime suspend. So, I was hoping I didn't find it, but I did. So
if I understand,
Yeah, but that looks broken.
so yeah, I know.
So really, and I can tell you that from doing 20 years of this, if you see something like this, analyze it and fix it. This is broken. Do not try to work around it. You're not making anything better. You make things worse.
So I guess the question is there any really use case for this call RCUX? And basically, is there anything that legitimately calls RCU and is waiting for that to finish?
I mean, if something waits for RCU to call back its queue to complete, it has to do synchronize RCU.
Yes.
So,
It
I
shouldn't
mean,
do its own.
or RCU barrier or whatever. The point is, if there's some use case implicitly assuming that something is happening magically before it can proceed, this is broken and we have to fix it. No point in trying to work around it. You're not making anything better.
Are we having three different? So we're having three different RCUs: call RCU lazy, call RCU, and call RCU expedited. Because that's going to be either way, we're going to have fun telling people which is which. But
No. The idea was to have an call RCU lazy and have the normal call RCU be expedited. So we need a lazy and an expedited. That's all we need. We just need the two, I would say. That we're just. But
No,
now you're saying that there's no reason we should have it just because if you need it, that means you need synchronize or RCU barrier.
Right.
Right.
And if some usage side is missing that, then it's broken today.
So, these patches delay the entire RC processing by like several seconds, like up to 10 seconds. But if we were to do something like call or, fix these bugs and then use Jiffy's till first FQS. So the point is we want to delay RC processing no matter what, whether we fix this or not, right? So, if we fix these issues and then we use Jiffy's till first FQS to see the same improvement, because we do see power improvement not having to call RCU at all or invoke the grace period processing at all for several seconds, right?
Yeah, you do better batching. No, I mean, but that's what happens. You queue the callbacks and you don't process them for a couple of seconds, and then you batch process them in one go, right? Because at some point you have to process them.
So we batch process everything, is what you're saying?
So if you delay the callback execution for a random amount of time, then once you go to it, all the grace periods have been done, and you batch process all the pending callbacks in one go, right? And that's where your power saving comes from.
No, the power saving comes from not even starting grace period processing at all. So it's completely quiet.
Yeah, power save comes when you actually stop make the noise. By noise, I mean that we invoke only one callback, and this is the biggest problem. And you invoke it with, for example, 1-2 millisecond interval. It doesn't make sense. And due to such noise, as I showed you on a plot.
Yeah, but you're describing the symptom.
Yes, it's a symptom, yes.
So let's talk about the underlying thing. I mean, if you have the callbacks queued by something, VFS or whatever it is, and then if you just delay grace period processing for a certain amount of time, you can go deeper in idle, and then at some point you have to do to end all the grace periods anyway. So because you cannot queue up callbacks forever, that doesn't work. I mean, you can queue them up and say, okay, if I have 100, I go and process 100. But you can't queue them out forever.
Yeah, memory pressures also.
Yeah, you're going to die hard at some point. So I think what you should aim for is delaying the dynamically delaying the callback processing so you get better batching. Because if you are awake and doing 100 in one go, it makes sense. But this also gives you a handle on busy systems, because if you see your queuing frequency is high enough, you're not going to delay because you risk starvation. Because if your batches get too large,
yeah,
then you occupy too much of the system. So you can scale that with the frequency of callbacks being queued. And if you have a synchronized RCU call, you have to do it anyway.
Okay. So you're saying that there's no point in delaying it by 10 seconds, just make it smaller?
You can even, I mean, this really depends on the system state. If your thing queues 5 in a minute, then go for 10 minutes. So, but at some point you have to decide to actually execute them, because you can't queue them up forever. So, but that's a very dynamic thing, and you can actually see it because you know the frequency, or you can measure the frequency they are queued. And then if you have a synchronized RCU call somewhere, I mean, you have to execute them because the synchronized caller is waiting for it. So there's no way out. But I think that's way better than trying to do a separate API, which people are going to get wrong anyway. Don't confuse users and kernel programmers. We do not need more APIs, please.
So you actually propose to get rid of caller CU lazy, and instead we should extend caller CU to do kind of dynamic flashing based on how many callbacks are queued and so on.
You can dynamically scale or delay the grace period processing.
Yeah.
And that's way more elegant, because you dynamically adapt to the use case. So in the case of a busy server system, you just never reach the threshold to go lazy or delay anything, because your backlog becomes horrible long. And on your idle Chromebook, whatever Android use case, you can just go for 10 seconds and the world is still turning, because you have only 20 callbacks queued.
Yeah, I think you've really given us something to think about, so we'll definitely look into that. We have only 5 more minutes. Yeah, Paul.
Just one possibility is for the system to learn what I think this is what Thomas was saying, but I'm putting it in a different way. What you've got is you're marking them in the source code as lazy. But you've got measurements you can take on latencies. And so you may be able to have something that looks at the latencies and figures out which one should be lazy and not at runtime, maybe. I don't know. In other words, if you let one be lazy and a latency goes out of bounds, say, sorry, we're not being lazy now. And remember that one's one that's not supposed to be lazy. And then, it's going to be a little more complicated, but it's going to be off to the side a bit.
Okay.
And it would build on the mechanism you already have. But it wouldn't require a whole bunch of people to come to agreement on exactly which one should be lazy under which circumstances. You could just have it classified on your platform for your use case. Is that what you're getting at, Thomas?
No, not really. So what I'm trying to say is, depending on the system state, on the number of queued callbacks.
Yeah, that too.
You can say, I only have 5. I go 10 seconds idle.
In their case, what they do is if they have even one non-lazy callback, the system's not lazy.
Right.
So
So, but if they have one stupid callback queue, they can just go 10 seconds idle, and if they have 10, they can just batch process them.
As long as it's not something.
Right.
Of course, there are some synchronized RCU that.
Yeah, I mean, synchronized OCU, you have to process them in order to make progress.
And there's some other
Makes
ones
sense.
where.
So in terms of, I guess I just wanted to quickly go over the point of like using tools and in terms of how, can we improve our tools in any way to find these issues so that we don't find them much later with through traces like, so RCU top is one effort in that direction where we want to show the callbacks queued and executed and all that kind of stuff. But maybe perf or something, there's a perf sked. Does it make sense to have a perf RCU that does this sort of thing? Or another thing I was thinking of, Yogini is a great tool that shows a lot of data. So maybe we can add some stuff to Yogini, you know, to show some of these problems. Want to talk about your tools?
Oh, but yeah, it's fine. So
Maybe a kernel shark as well, right? If kernel shark can like show ticks disturbing idle or something. Just Steven? Oh, thanks.
yeah, for analyzing, we have trace CMD, we have perf, we have kernel shark, and then yeah, plenty of tools.
I noticed you're using kernel shark 0.99. Please upgrade to kernel shark 2. It's got a lot more features and it doesn't have that stupid, you notice like everything got crunched down to one side. That's a bug and geez, that's it. That never made it to 1.0. What? 1 point or a point. The latest one does? Oh, well, we're 2 point something now, so try that. Yes, so yes, it's great. It's going to have a lot more things and for Kernel Shark. By the way, Jordan Kardajov is the new maintainer of Kernel Shark. So we have a bug report. If you go to kernel.org or there's a bugzilla.kernel.org, go to tools. There's a trace command Kernel Shark. File your bug reports there, please. Thank you.
Visualizing some of the issues.
Yes, yes. We have plugins, lots of plugins. I'll be talking about that at Open Source Summit.
Thank you, guys.
Back 10 after 12, I think.
Hey, you.
Okay, yeah, starting again. We have a couple of, two traditional topics. First one is Valentin, so yeah, take it away.
All right, thank you. So hi everyone, I'm Valentin. Despite wearing the one company swagger, I am working for Red Hat. I'll be talking about jailbreaking APIs. There is some overlap with what Marcelo has already talked about, but hopefully I do have some new things to say, or different things rather. So yeah. So yeah, nothing new with what Marcelo was talking about. If we care about CPU isolation and know how it's full, you have a set of CPUs where you really want nothing but user space task happening. So if we then look at what's happening in terms of APIs, so software visible APIs, you could have some architecture feature that is interrupting everyone, but you can't really see it. So it's more about what are we doing in a kernel that is causing the interference. So if we look at SMP calls mostly. So in that little graph there, I have the results of tracing a simple benchmark that's supposed to represent what happens when you are using CPU isolation. So you have skipping CPUs in green. That's the stuff that's supposed to take care of the housekeeping work for the isolated CPUs. And the isolated CPUs are just running a simple buzzer loop, always in user space. So you never want to leave user space, and anything that takes you out of it is interference, pretty much. So you would expect that, like this is 20 minutes of tracing, nothing would interrupt those isolated CPUs, but as you can see in red, you have IPRs that are hitting those CPUs. And I can talk about what those are. So the first one, or like the major cause of that, is actually pretty stupid. That's an x86 box, and that's what you're seeing here. You have like those 3 bars that are the longest ones. It's just the 3 steps of insertion patching on x86, where you do a step, send an API to everyone, do the next step, and you have 3 steps in that process. And in that case, it's actually a static key that is repeatedly being flipped. If you just look at the name, it's supposed to be static. So if it is being repeatedly flipped, something wrong is happening. Just digging into that specific case, it's caused by an NTP daemon that creates a socket with timestamping enabled. And it so happens that timestamping in the socket world is gated behind a static key. But seems like that there's really just that NTP daemon that's using that. So NTP daemon does that thing with that socket, destroys the socket. Sometime later, we destroy the socket, disable the static key, and you just keep repeating that pattern. So we actually we are looking at how to make that better, because clearly this is a case where, yeah, we could make that better. The other one is actually TLB invalidation. So Marcelo and Frederick already briefly mentioned that. And there are patches out there to defer that, because clearly here, if this is kernel TLB invalidation, we don't need to bother user space about it. We could just say, okay, next time you enter the kernel, do this operation that is just for the kernel. So the 2 patches I have, or the 2 series I have listed there, the first one is kind of prerequisite work about making context tracking a bit better. I think it's actually in now, in 6.0. And the other one is kind of an older one from Peter, which I think was mostly for live patching. So there were some things in there that we're actually looking at instruction patching. So if we are patching instructions in the kernel, we don't need to, again, bother user space immediately. We could just say, okay, remember that, and then next time you have a transition from user space to kernel, do the patching. Of course, you do want that to happen as soon as possible, because if you start delaying it a bit too much while you're entering the kernel, you might miss the patching that you needed to happen. Marcelo mentioned that Nicolas also worked on that, so he took that thing of deferring work to the next transition to also apply that to kernel TLB invalidation. And so in that case that I've shown in there, like it does actually work out pretty well, where we don't see any interference anymore. But the point I'm trying to make here is this is pretty much reactive, right? We're taking one specific system with one specific set of workload, and we are seeing what's happening. If you just do a stupid grep of the kernel tree, you have, well, in there, you're gonna get like stuff in comments and documentation, but you have at least like 400 call sites of SMP calls. And it's quite difficult to reason, okay, which ones make sense, or I'm really in the scope of stipulation. Which one could cause interference? Which ones are just caused, like Marcel was showing, by user space? So you could say, yeah, don't do that. So what I try to do, I started with coccinelle because actually, it might surprise some of you, but I actually do like coccinelle. When it works, it's really nice. When it doesn't, yeah, okay, you start screaming at the computer. But the idea was, okay, so we have all of those call sites. Can we try and make sense of the ones that we know will not interrupt or send an interrupt to isolated CPUs? So maybe we can realize that, oh yeah, we have this SMP call, but further up the call stack, we actually like checked either a CPU argument or a CPU mask argument, I guess, in housekeeping helpers. And then that got help us reduce the search space. Just doing that, so like explicitly seeing a housekeeping helper somewhere in the call stack, that doesn't reduce the search space by a lot. There's like 3 files that are removed out of the hundreds. What I've realized is most of the places that do the right thing do it out of line. So it would be like if you have a CPU mask or CPU argument in a struct, like when you initialize your subsystem or your driver, you will check that against the housekeeping helpers. And then in your actual call site, you're just using that. But using coccinelle, I haven't found a nice way to tag that and expunge it out of the search space. So what I've done is the only other option I saw, which is list all of them, try and put them in different buckets and go through each bucket and try and classify them and see if we could find patterns. Could we do something that would apply to each of those patterns? So the first one is just, yeah, you interrupt the CPU because you want to fetch something that is just local to that CPU. I've tried listing different call sites that all have kind of different requirements. So first one is kind of regular read that is caused by reading into CSFS. You read something into CSFS for specific CPU ID with or specific CPU. That's going to send an API to that CPU to fetch the data and send it back to you. So for that one, you can have an argument, well, don't do it, which, okay, it is an argument, but it's not always as easy as that. The other one in there is for perf. So if you have an event that is programmed on a certain CPU, that one, well, you kind of have to do it. You can't really, if you're thinking about deferral, you don't really want to defer it because you do want to interrupt the context. But so these two first, you could say, yeah, it's like, it's user configuration. Someone asked for those to happen. The third one in that list is not really in that category because it is used internally in the kernel. So that's for ARM64 frequency invariants. So if you, I think that's on ACPI systems, you're gonna end up on that. And you could just send an API to a CPU to collect the counters that are used. It's just like for x86, like APEF and MPEF. You look at what's the average frequency of a certain time compared to a fixed counter, and then you can try, okay, see which frequency we've run at and then feed that to the frequency invariance engine. Again, another argument you can have is, well, if you're running CPU isolation and you really care about latency, you probably are not using DVFS. You could just have a static governor in there, but that's the patterns that I'm seeing. And so one thing with those patterns that I think we can improve is if we encode or if we better express the intent of the SMP call, we could, well, first of all, it will make like greping and documentation a bit simpler, but we could also like apply, well, some countermeasures to each of those patterns. So if you're fetching data or data for a CPU, you have the case, for instance, well, CSFS reads, it kind of falls into what Marcelo's been talking about. You could just have a thing where you say, yeah, I don't do it. Like maybe I return an error or I print a warning, but I don't let that happen. You could have other cases where, so for instance, for the internal or in-kernel use of this API, you could, okay, do it, but you do log it somewhere. You print a one, have a one once, or have a new trace event so that you log it somewhere. You say, yeah, I've done it, but in the future, I should really not do it. Can you think about doing this any differently? If I take the APEF MPEF example, for instance, Thomas modified that not too long ago, and it's a bit better in that you never send an API, just since you always log those counters at the tick anyway, you just record how long ago you recorded that, and then if that's too long in the past, you just return like an error value or a known default. That makes sense. So you collect your data periodically, and then if you are asked to get it for a certain CPU, you just return the last known good value, so you don't cause a new interference. Another one is about synchronizing against a running task. So that pattern is more about, okay, if you have something that is taken into account when you have a context switch, and for some reason you could have a code path where you actually modify what is being taken into account. If you have a task running somewhere that could be impacted by that, you have to go and API it to like reproduce the code that happens at context switch. So a simple example, well, simple, relatively simple example for that is for ftrace. Is Steve here? Oh crap, he is. So you can, with ftrace, ignore events that are generated by certain PIDs. And that is actually taken into account at the context switch. So when you switch to a new task, you see, okay, should I consider this PID or not? If you update the list of PIDs that are ignored, then to make that work, right now the code just interrupts all of the running tasks and to make or to reconsider that or reevaluate that field. So that's, in my opinion, like a good candidate for the deferral to the next kernel transition or user to kernel transition, right? Because for ftrace, if it's purely user space, you don't care about it. So for things that match to that pattern, we could say, yeah, okay, I just package that into something that will happen as early as possible in the next user to kernel transition, rather than cause interference. I kind of have a counterexample to that one, so that's for rest control. So that's for x86. I mean, there's a few things, but mostly like cache partitioning. So you could change at runtime your partition, and then what it does, it sends APIs to the affected tasks to update, because it's driven by a CPU register. So if you change something about the cache partitioning, the running tasks need to be affected by that. So you could argue that you do not want it to be deferred to the next transition. You want it to happen immediately. And then there's always the other side of the argument, which is, well, if you care about isolation and interference, and you're using rest control, you should just statically partition your system and then don't modify your cache partitions later on. I think what I'm trying to get to is, for all of those, we probably want either an argument or two variants. One is, I know I can defer it or I can not do it. And the other is, we should probably do it when it's invoked, but we need a way of logging those and potentially refactor the code and modify it so that it doesn't happen in the future. And the last category is kind of the catch-all. I kept modifying the slide to try and split it into different subcategories, but I think it's pretty much just, yeah, there's no magic solution to that one. It's kind of a use case fix. So I've mentioned instruction patching for x86. So in a general case, that's not a problem on ARM64 because we can just patch the branch. We don't have to send APIs. For x86 with this 3 API step, that's a problem. So that's a thing that could benefit from the deferral patches, only if, yeah, we're patching kernel code. The other big one is kernel TLB flushing. That is more of a, we don't have an architecture feature to do it for us, so we're just IPing all of the CPUs, and we have the per CPU instruction to do it. Again, for ARM64, there is an instruction that we do it for the whole system. Doesn't mean it's better for like interference and latency, because it is going to impact the isolated CPUs, but at least on the IPI setting front, we're a bit better there. And then, yeah, general synchronization. So for instance, for CPU cache tuning and shrinking, and all the places, there are things where we want to interrupt all of the CPUs at once for synchronization. I'm not exactly clear on why is it required for that specific cases, but it's like a pattern that is spread in quite different places. And that's, again, I haven't found like a nice argument where you can say, yeah, there's a generic rule that applies. Some of them are, yeah, even if that CPU is isolated, we do need the thing to happen. In some cases, not. So I don't really have a solution for that one. Like I said, ask Santa and wish that someone can fix it. I think that's pretty much all I have. So if there are any questions or comments, that's the moment. Oh.
Ooh, that was not good. That was painful. That was do that. Well, this isn't going to work for me. Can you hear me? No, I mean, I unfortunately, because I was putting out some fires, I came in late. So on the deferral side, I mean, I didn't get to see a chance of seeing what the mechanism is to acknowledge, or I mean, to call this stuff. So in other words, I'm perfect. It totally makes sense. So like if you had some sort of interface or API where I can just say, execute this on all non-user space if you could really make it sure with all the race conditions between user space and that. So I could say, this will go through and set an API, or I could say, I guess you would have to say, anything that's in user space, call this now when it gets back. And then you set that, and then you say, for everything else, interrupts, send an API to. I take it that's what you have? You have an interface for that?
So that's the default patches that originally were from Peter,
Okay.
and Nicholas has picked up.
Because for at least on the F-tree side, I'm perfectly fine with that. I can't speak for the other aspects of the kernel, but yeah, it makes, I mean, I had what you said, your description of what the event PID write does is exactly right, which I went back and looked at the code and said, oh, I commented it pretty well. So I guess.
Thank you for that.
I was like, yeah, because I forgot what it did. I don't comment for you, I comment for me. Because I always forget what I did when I write code. But no, yeah, I'm perfect. I'm okay with it, the approach.
Okay.
So I don't really have any other comment. Anyone else? Yeah. Well, throw it upside down.
So you have any thoughts on how this might apply to RCU, because there's IPIs flying around for expedited?
Yeah, so I looked at RCU buyer. The thing is, let me try and remember what I looked at. I think you skip, well, yeah, you skip CPUs that do not have any callbacks and queued.
Right.
But then if they have any, I think you do IPI them. I think that kind of falls in the, you need a specific solution for that. So yeah, because you do end up interrupting isolated CPUs if they have callbacks and queued. I don't know if you could actually just directly send an API to the offload thread rather than directly interrupt the isolated CPUs. I know that I have a note somewhere that I should look into that. But that's like, yeah, that's specific to RCU buyer. And that's kind of, that third category is, yeah, it's going to be solutions that are specific, unfortunately, the call side.
The expedited IPIs, expedited RCU also uses IPIs.
Yeah, so those I just said, yeah, that doesn't make sense to have those in like isolated scenarios.
I'm just making you aware, I guess. You probably looked at it, but the expedited RCU and then barrier, like you said, and then there's also there's emergency IPIs that go out if CPUs are not reporting question state.
But that, so is that just for stall detection, or is that
it's
forcing
for,
the quiescent state?
I think it's in certain configurations, and the comments say like it's used to loosen things up a bit if the CPU is constantly spinning in kernel mode.
Okay. Well, which shouldn't happen when you have your user space task running isolated. Have a look. Thanks.
Okay, sounds good.
General sort of question. Since I seem to actually have found lots of stuff to potentially fix, or at least you understand, I guess, lots of the sources, what will be the next move? would you personally start maybe introducing the more annotated version of the codes just to be sure that one catches everything, or would you, I don't know, start fixing the problems that we already know are problems?
Yeah, so I think I'm gonna do both. Because there's clearly the NTP thing, like with the static key being flicked repeatedly. That's something that's a button that needs fixed, that needs fixing. But then if you want to fix the thing with ftrace for the PID write, that's a bit more convoluted because we do need the context transition deferral patches. I think I might just start with, well, probably have a chat with Marcelo and look at, just for instance, for the data fetch, see how we can go about that. I could do just this annotated version and then merge that somehow with what Marcelo has been doing and try and get forward.
And do you think we can do anything to try to flag a new introduction, new, I don't know, patterns that can actually introduce problems? So recognize when that happens. I'm not sure how that might work.
Yeah, so I think I still want to experiment a bit more with coccinelle on that front. But yeah, I don't know how far I'll be able to go on because I mostly used it to try and reduce the search space. I haven't used it to try and do the category or the classification. Well, I did briefly, but I think I could get back to it and try and see if I can at least get it to maybe warn about, oh yeah, you should double think about what you're doing because that could cause an interference. That would already be a good start, I think.
Now that I think of it, maybe, if we reintroduce the new, let's say, API with the, where you actually have to declare what you're using APIs for, and then maybe if that's the only API one can use, so we basically kind of remove the generic
right,
one.
yeah, so you are forced
then
to
you are
think
forced
about,
to use it, and then we can probably evaluate better. I'm not sure if
yeah, the thing is for that third catch-all category, it's kind of how
Yeah.
do you really categorize that? So, but yeah, that's a good point.
So for the pocket one, I think what we did was to have a daemon. Not sure if you've seen the daemon. The
Yeah,
daemon
I've seen that thing.
It's yeah. And I think maybe the Faro patches would handle that case, And
In that specific case, they would, yeah, because actually the one patch from Peter, I think it was for live patching, and I was specifically about instruction patching, but it does feel like in that case that it shouldn't behave like that.
Yeah.
The static key shouldn't be flipped several times a minute.
Yeah, and then the other thing I wanted to mention is that I saw some infrastructure on x86, new infrastructure to do remote MSR reads. And I think that maybe you could handle handle some cases through that interface. And I'm not sure whether that interface would inflict any latency impact, but that's.
Yeah, I think that's another argument is if you can implement the mechanism without an API, do you actually still want that thing to happen on an isolated CPU? Because it might not be, it might be lower interference because it doesn't cause an IPR, but it could still cause interference.
Right.
So maybe you actually still want to have an SMP call, but that will never perturb the isolated CPUs. I think.
I think there is an API when you install a perf event on a running task. And for that one, I don't think you can use any deferral, for example, because perf events also
you want them to
profiles
happen in the
user
context of
space.
the tasks.
Yeah.
I think that one falls more into don't target tasks that are
Exactly.
isolated. That's, yeah.
It doesn't make sense, for perf anyway, because perf is when perf runs on a CPU or for a process or something, it's going to run NMIs. It's going to be interrupting it constantly. That's how it profiles.
Yeah.
It interrupts. So it doesn't. It's yeah. I don't think we care. I think it's one of those. Don't do that if you care about it.
But maybe we still have the option of like using a different interface that does the same thing, but at least that documents that, yes, we do want that thing to explicitly happen all the time.
Yeah.
And maybe log it somewhere.
Well,
if you
no,
want.
it's not that we don't want, it's not that we want it to happen all the time.
Oh, it's just that it's
It's just
how
like,
it's supposed to work.
It's like, okay, we're going to make sure we don't send an API to it, but once we enable perf on this task, it's going to trigger a bunch of NMIs on that task.
Yeah, it's the frequency, the cycles, events, but there are some software events, even trace points.
Well, so basically if you enable tracing on, so now it depends on what you're enabling on that. So, but a lot of that, okay, I only use perf, I don't use perf for trace points, so that's why to me, I don't care.
I guess. But anyway, it's kind of a corner case.
I guess there's really there's not many cases where we really need an API on a user space. I think the whole thing is like, what's the overhead the whole problem with context, the switch between context between user space and kernel and tracking that is you have to hit the fast path. And any little change you do there is noticeable. And the whole pushback of the doing it is the overhead. So you can actually thank Meltdown, because Meltdown caused the overhead of system calls so drastic that as the strace maintainers once said, after Meltdown, the performance impact of strace has shrunk tremendously. But other than that, I'm interested to see what the, do you have?
There's a link actually on the slides. I think the second one in there, that's the original link, the original patches from Peter. The thing from Nicholas is somewhere on GitHub. I can send you or put the link somewhere.
And they have the performance impact on it?
I haven't. Maybe Nicholas does.
Okay.
But yeah, he's not at Red Hat anymore. So.
From the isolated CPUs, there shouldn't be a really visible performance impact because we take advantage of the context tracking RCU atomic fetch.
Well, actually, that's true. This is only for when that's compiled. The context switch is compiled in.
It's only for those who send APIs.
Yeah. So basically, if you care about isolated CPUs, you enable this, which means that you don't you're going to. I don't want to say you don't care, but you'll take the sacrifice of the system call performance impact due to tracking context for this. But for those that don't care or that care more about system call performance than isolated CPUs, this could be turned off. Is that correct?
Yeah, I think if you don't have the Hertz full, that's not compiled in.
Yeah. Okay.
Just to clarify for me, so basically what this is going to do is it's going to defer all SMP calls by default, and then specific sites will.
So no, the way the series is at the moment is you have very specific users of the SMP calls that can be deferred. So with Nicholas, I think it's just instruction patching and the kernel TLB invalidation.
Okay, so only those will be deferred.
I mean, that's the state of the thing at the moment, but we need to know what we want to do there.
I see a lot of similarities between this and the caller seal lazy stuff in the sense something similar, like we want to encode the intent in the API. Thomas said, don't add more APIs. No, I don't know if that really applies to this because SMP call is more specific to use case maybe.
I don't know, Thomas.
I mean, the instruction patching, the static key one, yeah, okay. The second one worries me more. TLB invalidation. The OR case is where you actually have to do that immediately. Otherwise, you end up with stale TLBs, which is outright dangerous. Remapping is one of the pieces you really need to do that immediately, because you can't have the cached stale TLB entry on one CPU, which belongs to the same VM space, because it's going to fiddle in something which it shouldn't. So you really have to be careful about the TLB stuff. That's a dangerous area to walk into. So for the static key patching, yeah, I mean, why do we need IPIs for that at all?
So I'm not extremely familiar with XCTC because
You know,
I come from an ARM
we
world.
do not IPI on static key changes, at least not to my knowledge. We shouldn't.
Is that because of the text poke?
Yeah.
Okay, so the IPI's IB is, I think that's just to insert memory barriers. So the way context tracking, or the way we modify text, is the breakpoint where
Right.
you have to make sure all CPUs see the same state. So we only send the IPI to all the CPUs to make sure that they all see the same
Yeah.
state.
Do we really have to?
Well, we don't have to if the kernel is in user space, or I mean, if the CPU is in user space. It's only because it's live kernel patching is only for kernel space. So I might assume that it's a memory barrier when you go from user space to kernel.
Yes, that's fully synchronizing.
So we don't need to. So if we could prove, or if after we make the patch, if we say this is in user space, we know we don't need to send an IPI to it. In fact, we don't even need to do anything. As soon as it goes in, it actually does. It's just a memory barrier. That's all we're doing is we're forcing a memory barrier on all the other CPUs. That's all we're doing.
Just trying to figure out whether we need it at all.
No, it's you're modifying code, and the whole idea is if it's cache lines. So if the CPU pulls in half the instruction and not the other half, and then executes it, it will crash. It will do a general. No. That's F-tray. No, this is modifying the code. We're actually, it's like F-tray, the function tracing, static calls. Anytime you actually modify the text, what you do is, the way it does is, we put a breakpoint at the first, so byte instruction. First byte, we put a breakpoint. So anything that hits it, because it's a no op to an instruction, or it's when we're changing something, we just emulate what we're changing. So at the breakpoint, we change everything. But we have to make sure everything sees that breakpoint. So we send an IPI so they all see the breakpoint. And then we modify the last 4 bits. This is where the tricky part is. We can't let anything see those last 4 bits, or 4 bytes. I mean, if anything sees those other 4 bytes without the first one updated, or anything mixed in between, it will crash. So we update the 4 bytes at the end, send IPI. So now they all see the same 4 bytes at the end. Then what we do is we switch the breakpoint back to the new instruction, and then we send the all IPI so we know everything's synchronized. Now, if the thing is if something's in user space, we don't care, because it's not going to execute that kernel code. So there's no reason to send the IPI, and as Thomas just said, the switch from user space to kernel space is the synchronization point, and it will see whatever we did at the time.
You should see.
Oh yeah, I guess as long as it's a synchronization point, we don't care.
Right.
And yeah.
I have to read back on the internals, but it should work.
It sounds to me that the point is, once we find whether or not if it's a synchronization point, it sounds like it could be delayed, and we don't need to send an IPI.
For isolated CPUs, yeah.
Or for any CPU that's running.
Oh, that's in.
Yeah,
CPU
you can't just delay it. No, you can't just delay all CPUs. You have to, but you could delay anything that's in user space.
You can't just ignore those which are in user space.
Yes.
You just have to make sure on kernel entry that you synchronize.
That sounds the same
So
thing with the
that
F-trace stuff.
needs some entry changes because you it might come in during patching, so which makes the whole do not IPI erasy thing. So you have to have some something ensure that this doesn't get into a race to hell, but it should be doable.
Well, I was thinking that the context, the stuff that we use like for RCU full and stuff, the context tracking handles the synchronization to say that, yes, this is, at this point we were in, or we're definitely in user space at this point. Or, I don't care if we are just, or we're transitioning, but I do something, and then I want to make sure that I was in user space after I did something, kind of like an RCU type of thing. And then I don't care. After this point, I don't, as long as if we're in user space at any time after this point, I don't need to do something else now.
Yeah, it should work, but it needs some thought.
Okay, or verification that does work.
There's some dragons as always, but
Yes.
it should just work.
Yeah.
The TLB invalidation.
Yeah, that one I have no idea how to do.
So, I mean, the thing is, if you know that, I mean, we are trying anyway to be careful about not IPIing to CPUs which do not have the same page tables loaded.
In some of the calls, yes, there are some that just do like API everyone.
Yes, there are some reasons why you want to do that. That's a tough one. Don't change page tables.
And just a question about the TLB thing. I'm saying for right now, are you just care about x86, but what about other architectures?
So I've only really looked at x86 and a bit at ARM because that's what I actually know. So on ARM, it's with an
obviously, I'm looking here. Sorry. I forgot who it was.
There's like I think TLBI instruction. So and that affects the whole. Well, I was going to say the whole system to make it short. Yeah, the whole system.
So my question is, with TLB validations, is page tables enough? Don't some architectures with tagging and such allow TLBs to have page tables for different? Or is it only every time you change the page table, does it always validate the entire TLB?
It depends on. It's very architecture specific.
Yeah.
And even on, it depends on, even on x86, it depends on whether we can, we have just page tables or we can use ACIDs. That changes the game as well.
Because it sounds like you never really know what's in those TLBs.
Kinda.
It sounds like there's more dragons.
But ACIDs makes it more complex because if it was switched out, if it switched to ACID space and the ACID is still valid, it still might be cached. So that makes it even more nasty. It's all a minefield.
Right, more time. Right.
All
Thank
right.
you, Valentin.
Thank
We
you.
are out of time. Thank you. And last one is Daniel.
So, hello, I'm Daniel, and I'm here today to talk about a tool that is helpful to measure the things that we are being talking today, which are sources of interferences and sources of noise. So the noise is an AGPC metric that refers to the noise that applications or that operating system imposes to a workload that is supposed to be the only one running, right? And DOS noise tracer is a tracer that tries to measure how much OS noise this tracer is suffering from other applications. It can be either in the kernel or any application in the on that target CPU. So this tracer in specific, it's not only the tracer, but it is the tracer and the workload. So the tracer simulates the classic AGPC use case, dispatching a thread per CPU, and this thread busy loops and tries to try to detect when there are two reads of the time that has bypassed a threshold. When this threshold is bypassed, it says that there was a noise here. So the workload, it does this measurement based on the time that was stolen from it. So that is the view of a workload running. But together with the workload, we have some instrumentation that we do that we hook to some trace points in the kernel, and we can extract information from that. And one of these information is how many times that thread was interrupted, either by an NMI, an IRQ, a soft IRQ, or by threads. So anytime the workload, it reads the time and how many times it was preempted by any kind of task that we have on Linux. And this is helpful for debugging. I will show some outputs of the tool. It will be easier to understand. So it traces this noise of these tasks that can happen on a CPU, and it also aware of the nesting that we can have. Like I can have my workload being preempted by a thread that can be preempted by an IRQ that can be preempted by a NMI. So and all the traces that are generated by this tool, they are aware of these, and they are all the computation to remove one interference from the other. So the idea here is that I can interpret as much data as I can in kernel, so I can read those trace points clearly without having to waste the time going back and forth on the trace. But I will show an example of the output. And there is also a user space tool, which is the RTLA, that does an interface for this trace. So here is the basic summary of the tool. I can go to the tracing interface and enable it. And after enabling it, I can see the summary output of the tool. So it says here that the tool was able to take this amount of time. Here is in seconds, right? In microseconds. And in this amount of time, the total noise that the tool perceived was this. And here's the percentage of CPU available. And among all these noises, the largest ones are this. So this is the sum, and this is just, okay, from all the noise, what is the maximum one? But because I also do, the tool also does this instrumentation, it can also say the sources of this noise, right? It can say it was hardware. Oh, and that's a thing I'll explain later. If it was an NMI, an IRQ, a soft IRQ, or a thread. So why I'm saying that there I have here the hardware, right? Because here's this one is the summary that is printed periodically by the tracer. But I also have a set of trace points on this tracer that prints the occurrence of any source of noise. So for example, here I have an IRQ noise from the local timer. This is the start time and how much time it took. And once the workload detects a interference that was higher than a given threshold, it will print it as well. But instead of only printing the time that was stolen from the from this application, it also prints how many interferences occurred to cause it. So in this case, this 8 microsecond interference was caused by these two previous sources of noise, right? The IRQ noise and the thread noise. And this interference number is synchronized inside the kernel locklessly. So I'm sure that it was just these two, one here that caused this interference, and not the previous one. This is useful while debugging because it removes sources of doubts and discussions of why this happened, right? But because the tool also sums up the amount of interferences, I can get cases when the hardware caused the noise. So if no interference happened and the workload was preempted, I can safely point the culprit to the hardware. That can be either in the real hardware when like the thermal throttling happens, or when SMI happens, and or virtual machines when the gas is preempted. So the tool already works, right, for some case, but it's a pretty new tracer. It has less than 1 year. And there are some requests that I see from people and myself as a user. And and I would like to get feedback from people to know where to start and get also help from the people to improve this tracer. So the things I heard more about what is missing is the thing that we have been discussing here, IPI tracing. So here I can see that this noise happened, but I don't know who generated this noise. And also, I will enter in each of these topics there, but and also integrate with workspace, with virtual machine. I have been talking with Paulo Bonzini about this, and integration with CI. So regarding user space, so the workload that I have now, it's in kernel. It's good, but it's only measuring the time that was passed. And many times the OS noise doesn't measure only the time, but the work that the tool was able to do, like processing a given kind of workload or processing packages and those things. So it would be useful to transform the tracer something generic that I could plug any workload on it. It has one downside, that I will lose the synchronization between the kernel trace points and the workload, because I can do this locklessly inside the kernel, but I do this using local CPU variables and barriers. I would lose that, but I would gain the benefits of running any workload with the tracer. And one of the challenges doing this, the first one is that I would have to have an interface to register this workload. So nowadays I have a structure inside the kernel that says that this is the PID of my kernel workload that I consider my workload. I need to find a way to add an interface to overwrite that information. And add, for example, the PID of the workload that I want to measure. Steve? So one of the possible interface I was thinking was a file inside the tracefs that I could register the PID of the workload. By default, it would be the PID that I create in the kernel.
So by default, like you said, your PID. So basically, you just want to be able to say, I want to monitor a single thread that's user space.
Yeah.
For everything. So kind of like, yeah, I mean, we have the event PID. It's basically like set event PID. So can you just put set work PID? I would say set, call it set. Keep the naming convention the same. But yeah, we do that for ftrace. We could trace a single event from tracing. We could set a single event from events. Since OS noise, I have no problem with keeping the same. It's already been done. There's precedent.
No, good. So one of the points is that for this workload, we need to do things like this workload needs to be pinned to a CPU.
Can you have a separate, okay,
Because
so,
if
well,
it-
well, wait, so you want the, so wait, the PI, so you're setting a PID here to set the workload, so what you're monitoring, correct?
Correct.
So what are you're telling it to to set the affinity of the workload or set just the tracing of the PID or the CPU?
No, because generally this use case, we have the workload pinned to a CPU, but yes, we might have a set of tests that we're monitoring.
Well, first of all, well, there's task set.
I don't see a reason why you have to pin it. You're looking at the kernel knows when the PID or any of the threads belonging to that process you're interested in or on any CPU. Just schedule out, it knows it as well, so you get it. So you get it via the TID or PID or process ID, whatever you call you go for, and it doesn't matter on which CPU it runs.
Yeah.
I mean, even migration is a noise.
Even migration is a noise.
Yeah, so-
even migration is a noise.
So I mean that I wouldn't restrict it to be pinned because that's a totally different decision. I mean, you might want to see the effects of can I actually afford migration?
Yeah. Yeah, no, I haven't. I
Because-
was limited because of doing implementing the kernel, but yes, I can also lift that restriction.
Yeah. So I mean, all you need is filter on the PID
Okay.
or
But
on
then,
the thread ID, whatever you choose.
Task ID.
but yeah, but thinking aloud, I could have two tools that I'm measuring the noise, one preempting the other. I might have to do with that case if I allow migrations. If I have, because I can have two workloads in the same
Yeah.
CPU.
That's reality.
Yeah. Yeah. No, but this makes my life easier because I would not need to.
Reality ruins everything.
No, in this case, it helped me. No, because if I had to force pinning the CPU, I would have to take more care and mess up with the CPU masks and like setting the tag in the task struct saying do not migrate it. This is a pin.
This sounds like an implementation issue, not something that should be exported to the user space, so I think, or to the
Yeah.
interface.
Yeah,
Right now-
I can leave. I think it's just better to lift these restrictions.
So,
And then when the task dies, I just return to the kernel workload.
so if you put in two tasks into this workload, question, like you said, and they interrupt each other, I mean, the output that you have, is it per task that you have? So you say this task was interrupted, so does each task have its own like structure of information that's being,
The point is that now I'm measuring things more on a per CPU basis. I'm not, yeah.
You don't want to look at it on a per CPU base. You want to look at it on, because that's global. You want to look at what happens in the context of a monitored task. So which is, it starts where you get scheduled in or in principle, it starts when the wake up event happens, and then you have the noise until you get scheduled in, the noise until you go out to user space,
Yeah.
and then anything up to the point where you go back to schedule, voluntary.
Yeah, so, yeah.
Not the involuntary. So you want to pin it on the task because that's your,
Yeah.
that's what you're observing. You're not observing CPUs. I don't care when I have a single task which I care about, and what happens on some other CPUs is completely irrelevant.
Yeah, no, in
No,
this
okay,
case, I made it.
wait, let me change like what Thomas is trying to say to something else, because I think you're focusing too much on what the current default, which is the kernel workload, which is looking at this thing and the task PIDs, it sounds like you have, 8 CPUs, 8 tasks, each pinned to a CPU, correct?
Correct.
So The paradigm that Thomas is saying is, well, okay, the paradigm you're looking at is I'm looking at it per CPU.
Yeah, I know,
And Thomas is saying he's looking at it per task. But you're both, yeah, correct, because everything's pinned. So yes, each CPU has a task. So what Thomas is saying, let it migrate and only do the track. So by default, when you're doing it internal, you pin it will say, okay, by default for this standard, 8 CPUs, create 8 tasks, pin each one, so we see everything. But in reality, it's measuring it per task, not per CPU, even though you can see it that way.
No, I made this per CPU because the traditional AGPC use case is a per CPU task. There's a task model that is in this way. And generally, people use task pinned to CPU in the use case that we're
Yes.
seeing, for example, at Red Hat customers.
Yeah,
but
but
a more
that's-
general use case would be per task.
But that's simply covering it, because if you look at it at it per task, and policy for the task is to be pinned, then you will see all noise events on a particular
Yeah.
CPU in context of that particular
Yeah, but
task. So
it's more generic and it's more,
yes.
It's a
So
win-win.
you're not inflicting any constraints on the workload. You can just use a free-floating task and figure out how well that behaves, depending on.
Yeah.
And for HPC, where everything is pinned, fine, it just
What-
works.
What I can do is something similar to what we added to the hardware lab, which is having modes. We can have a mode which is per CPU, and we can have a per task mode.
I don't think you need that. I mean, you could just, like you said, if you care about per CPU, you just pin everything to a CPU. But really, I don't see any use case where you care about a task bouncing between CPUs and you care about each CPU, not the task. There's a hand mic too that Judy.
Well, I was just thinking that you can also have like equal number of threads to the number of CPUs. So if you're worried about missing noise on other CPUs or something, like don't pin it, but have the same number of threads and then let them migrate. I don't know if that aligns with your design or not, or
Yeah,
but it's just something to.
Now we dispatch the workload by the CPU mask, and the number of threads that we dispatch is based on the CPU mask. So if my CPU mask has 5 CPUs on it, I dispatch 5 threads. That's why I probably need a mode so I can register.
So, well, why don't you just, when you create it, you pin it, like you could do that and use, why have this interface force the pinning? You could just use task set and just set those things, or yeah, just have task set, each one gets it to its own CPU, and then, run it, or, so that could all be done in user space.
Yeah.
And just FYI, if you want to trace children, so basically you could put one PID in there and you want to trace all the children. That's the ftrace set, ftrace PID, and set event PID both have an option where you could say, okay, I want to set the children. This is that write PID that we're talking about with the FYI. That thing it does, there's a whole infrastructure there that will allow you, that it attaches to the fork trace point. So when it splits, it will add it automatically. It will add the child automatically to the list. And when it exits, it will remove it from the list. So you could just hook into that same infrastructure.
So
as
I
well.
have, so you're saying that you already have the infrastructure also to remove it from the list?
Yes.
And can I have a callback?
Yes.
Okay. Yeah, because that would be one of the points here.
And then, like you said, you want to trigger, like I saw that, you want to trigger.
Sorry?
Yes.
Yeah, the problem.
Yeah, that's already been done.
Good. So, another sorry, one of the limitation I said of the current tracers that I can trace when a workload was preempted, but I don't know the root cause of it. And I saw that on ARM we have these trace points, and there's these API arrays, and it points to any time a API is raised. So
it sounds like it says
somebody
that-
should should educate the ORM people with a large stick, because the trace point for sending an API should have been in the generic code where we actually have the functions to do so. And it's totally uninteresting which of the 5 gazillion variants of how to send an API on a particular incarnation of hardware you're using. So the interesting part is what is the calling context which actually wants to send an API via SMP function call or whatever, one of the reschedule API or whatever. So you want the caller of this to be traced. So the trace point should actually be in generic code and not somewhere in the architecture. That's totally nonsense.
Well, that's the sending of the, I think also you want the trace point in the API when it enters and when it exits.
That's different story. That's on the receiving end,
Right.
but we're talking about the sending
Are we talking
side.
about the sending of API or are we talking about the interrupting of it?
We do not have a trace point on the send side right now, but the ORM people obviously put one in and they put it totally on the wrong place.
Well, that's the API raised, right?
Yeah.
What?
Okay, that's where you're triggering.
Yeah,
Yeah,
that's my interest.
I mean, if you if you look at SMP function call, you go through the generic code and then you end up in some random place in hardware.
I can tell you why they did it this way is because looking at it, they grouped all 3 together. The raise, like they made it like a soft IRQ, raised, entry, exit.
Yeah.
And the only way to get the raise is in the, or not the raise, the entry and exit is in the architecture specific code. So they probably said, well, they probably did the entry exit and they just included the raise together. So that's probably what they didn't even think about putting it in the generic code because they probably didn't think it made sense to have just the raise and not having the entry and exit.
Yeah,
So-
it kind of makes sense, but it's pretty stupid because we have about 500 gazillion ways how to implement
I'm not
actually
saying that.
APIs.
So I think the solution is to move that trace event, those 3 trace events into the generic code and let anyone implement it. But then the 2 API exit and entry, they may not ever be implemented.
Right.
But they could exist, but never. Well, that's the thing is if you move it in there, the trace points will exist but not be implemented.
Yeah,
I don't think anyone wants to do that.
I mean, the question is, I haven't looked at the ORM implementation. I have to look at it. Whether that's a catch-all entry point, because on x86 we have different entry points for SMP function call or for the reschedule API on purpose, because the reschedule API is basically a knob, while the SMP function call has to do actual work.
So, I mean, what we need to do, because the way the trace points is, because they're grouped as the IPI group, trace schedule, or the trace event group is the IPI trace event group. So you really want them all in the same header file. So that's
Yeah,
why,
but then keep them.
I mean, we're just going to, so what we do is we can move it into the generic and put under each one, if def, IPI exit exists, or has IPI exit trace point, and put an if def around each one. So we have one, make it so with, like for the raise, we have one generic one that everyone uses, but because the exit and entry are unique, I mean, the raise won't need an if def because it'll be implemented there, but we can't have the entry and exit.
Except for UP.
Right, so, well, then we need an if def around it. So, because we don't want those trace points to exist if there's nothing calling it. Because people will say, oh, it has an IPI exit, and
But
then
it
it
doesn't.
never gets hit because there's nothing implemented on IPI exits or entries, and that will confuse people. So
We could hook them to the IRQ vector trace points. Then I run. It was a joke.
But that's why it's in the ARM architecture code only. But to move into the generic code, we'd actually have to put if defs around it. So it only gets implemented if actually something's hooking to it. Otherwise, they will get shown to user space and nothing calls it.
Cool, 0 APIs. We raise tons, but we never execute them.
Yep.
Zero cost, perfect.
It's kind of like the old, we're not going to test for COVID, so we don't have any cases.
Wait, I think there are more slides. Okay. This is the old version of the presentation. And finally, that's something that I've been discussing with Paulo Bonzini, which is nowadays we have like we identified the hardware noise as a gap in time, but we don't know what caused this noise. When it's a hardware, we might try to find some SMI counters and all those things. But when it's a hypervisor, we have no clue of what is happening. So one of the ideas is try to to integrate the hypervisor to notify that, okay, the DV CPU was preempted, and this was the cause of why it was preempted. So I could get an information. Okay.
Yeah, but you can do that on the host.
Yes, but I'm running it on the guest.
Yeah, so what you do is you run trace command agent on the host, and from the guest, there's a proxy, there's the new trace command. In fact, we do this, I implemented this just recently, where you could put the agent on the host and have the guest actually connect to it and say, give me events from you. So you get, the guest actually gets the guest trace.data and the host trace.data. So you could say, give me all the KVM events.
Okay, so the idea would be to not do anything in the guest, just trace and then merge these traces.
Yes.
Yeah.
That
It already exists.
All your problems solved again.
No, it's good. It's good. No, it's good. That's the idea. It's even better. So, and can I, do you have these options as in the trace command library?
Yes, it's part of trace command.
Okay.
They're 3.1 or 2, I think, just.
But can I integrate it on RTLA? To have a single, like to have a single point of entry.
We'll have to talk about that. Yeah.
Yeah.
It's we only have a couple minutes left, so.
Yeah,
not
no,
enough.
I will talk about this in the second part of this presentation, the real-time summit. Okay. And yes, just to finalize it, it's useful to know when the VM was preempted by the host, because we have all these CI infrastructure that they run on VMs, but we cannot like measure the OS noise there because you don't know if there's a problem in the kernel that we are trying or if it's in the host where we are running it. If we could understand from the guest that it was a preemption in the host, we could just discard that data and carry on and try to do CI on virtual machine. That's why it would be nice to have this information in the guest. Yeah, these were my points. I'm glad they are easy. That's it. Thank you.
Right, this was it. Was the last one? Yeah. Right. So thanks everybody for attending, and I think there is lunch break. And well, feel free to ping, I guess, everybody if you have additional questions. Thank you.
you.